Good evening to one and all present here. This is the 85th talk of Intersociety weekly webinar series. This talk is jointly organized by IEEE Kerala section, Institute of Engineers Kerala State Center, Computer Society of India Trivandrum Chapter, Project Management Institute Kerala Chapter, Intersociety Trivandrum Chapter, Vakkom Moulavi Foundation Trust.
Is it okay? Adila, go ahead.
Your mic is muted.
Adila, no, you go ahead. No problem. Go ahead.
Sir? Sorry, sir. Today, we have with us Dr. Arun Janarthanan PhD in Silicon Architecture Power, Qualcomm. This talk will be a turning point to all, especially engineers and researchers, particularly for engineering students. Here, our speaker is going to make maths fun and less daunting. So, every participant, please make sure that your microphone always remain muted. And you can type your queries in the chat box anytime during the program, which will answer at the end of the session. Now, I call upon Sai Krishna TS to deliver welcome speech.
Good evening, everybody. Am I audible?
Yes.
Good evening, ladies and gentlemen. It gives me tremendous confinement to represent IEEE family and to welcome each one of you to the 85th talk of Intersociety weekly webinar series talks. Let me appreciate the efforts of Harindra sir, co-volunteers and professionals of Kerala sections who are supporting this event in making this a huge success for the past 84 talks, bringing out the best profiles and presentations to the virtual room. Moving on to my assigned duty. Today, I find my immense pleasure to introduce our speaker, Dr. Arun Janthanan, distinguished figurehead in chip design product technology, to share his thoughts on the topic Demystifying Maths. Welcome to you, sir. Next, I welcome Harindra sir, Chair of Intersociety, the lead of IWWS, to this auspicious evening. I welcome you, sir. Next, I would like to extend my warm welcome to volunteers of today's session, Atla, Jacob Varghese, Amruta Aravind, Sumaya, to the 85th talk of IWWS. I wholeheartedly welcome all the co-organizing societies, the professional community, and the most esteemed participants to this wonderful evening. Once again, my cordial welcome to all of you to the 85th talk of the Intersociety weekly webinar series. Thank you.
Thank you. Next, I call upon Amruta Aravind to introduce the speaker.
A very warm good evening to one and all present here. Dr. Arun Janarthanan PhD, 18 plus years of academic and industrial experience in chip design product technology, PhD from USA, Silicon Architecture with Qualcomm and previously with Intel, California. 100 plus in-person and virtual talks, IEEE conferences, Intel and Qualcomm technology conferences, 15 plus engineering colleges, including premier institutes, audience totaling 10,000 students from Tamil Nadu and all over India. First principles thinker, crunching all of counting to calculus to Fourier transform in under 1 hour. Designs, DIY, connecting advanced science, origami, music, reverse working from the child's brain. In 2 years, reached 10,000 children in grades 1 to 12 and college across Tamil Nadu in personal capacity and through massive companies CSR. Foster a community of 200 brilliant kids, Indian families with yoga, martial arts, Indian music, dance, astronomy, and more. Research intern, low power architecture, Intel 2005, doctoral candidate, University of Cincinnati 2007. Power designer, Intel 2008, SoC micro architecture in the 2011, low power architect in the 2013, SoC power architecture, Qualcomm 2017, academic affiliations, board of studies member, alumni, Sri Venkateswara College of Engineering, Anna University, Institution of Engineers India, distinguished guest speaker, Srimati Visakha Hari, Proud of India, camp coach for 200 plus children, distinguished alumni, 20 plus talks reaching 5,000 plus kids in Alma Mater. A very hearty welcome to you, sir. Sir, you can take over the session now.
Hi, namaskaram. Thank you so much. I hope I'm audible and I hope my screen is visible as well. I'm right now finishing another talk at IIT Madras and I'm just heading back to my home. So it's a beautiful campus here and I thought I will give a nice walking presentation on my love for mathematics and science and technology, which I share with children. So thanks for the generous introduction. Again, my name is Dr. Arun Janarthanan. I've been in the US for about 10 years and born and raised in Chennai and Tanjore. Came back with, I have two children, 10 years and 5 years. We both, me and my wife, Anusha, we used to work for Intel in California. And then we now work for Qualcomm in Chennai. We switched to Bangalore and then we're back again now to Chennai. Chennai is our hometown. Ever since moving here, I had a thirst of simplifying education for children. How do I simplify education for children? What parts of education do children find difficult? My first pick was mathematics because mathematics was my love. It was very easy. How can I simplify math teaching? And I wanted to find out what could be taught differently in mathematics. So I asked themselves the question, where does everything begin? Can we rewind 1,000 years, 10,000 years, 20,000 years? When was the first time ever that humanity wanted mathematics and why? Which part of the world wanted questions? Who had questions to ask regarding mathematics more? Which civilization asked us more questions than others? And what could have happened at that point of time, right? A lot of questions were in our mind. So I'm sharing my screen now. I hope you'll be able to see my screen when I share it. Please confirm if you can. I'm just going to quickly walk through a couple of presentations and then show some simulations. So I hope you can see my screen now. You can see my screen now, right?
Yes, yes.
Excellent, excellent. So I'm sharing my screen where I'm actually showing a nice cave family which is far away in the west or somewhere, which wanted to understand mathematics. Does this cave family need mathematics? This is how I teach math to children, and they say yes. The kids say yes. Why? Because they had sheeps and they wanted to count. They wanted to count the sheeps 1, 2. But then there was no 1, 2 at all. How could they have counted? There is no number system at all. So they said, okay, let me just scratch 1 for every tally mark and just easy to count 5 sheeps. But then what will you do when there are so many? They started scratching these ones everywhere and they ran out of space. So the kids find it very amusing. And then I said there are Babylonians who came about and then who offered this, who offered special numbers, and they thought they were solving the problem. But then what happened was it was just becoming funny. Look how funny 59 is. Look how funny 40 is. The numbers were not invented still, right? I talk about this to children and the children find it very fascinating. They think of the period when the numbers were not invented. They're very happy because they have an opportunity to intervene there. They have been time travel to the past where children can actually present what it's in their mind. They start laughing with us. They enjoy this so much. And slowly what happens is I tell them that the whole world problem was solved by one country. And what is that country? Which country solved the whole world's problem of counting and how? Can someone help? It is India, right? Indians solved the whole problem of counting by inventing 0, and it is not 1. It is not 1, 2, 3. It is 0, 1, 2, 3. Right? So I kind of reinvent the whole aspects about numbers and all of numbers can place. Come back to my presentation, make my talk here, and then take a pause. Was my video okay? Was I able to share fine? Was the bandwidth problem okay? Or
Yeah, that's okay, but sometimes the sound is clipped.
the voice is breaking? Is it the voice is breaking?
Yeah.
I see the message. Okay. So I'll try not to move and I'll stay where the bandwidth seems to be very high. So I think this place is okay. Now it should be fine, right? Now the bandwidth is okay.
It is fine. Voice is
I
fine.
think so.
Okay, thank you. So now essentially, so we know that the number system is broken, right? We know 1, 2, 3 is not the right way to start teaching mathematics. It is 0, 1, 2, 3. The moment you say 0, I have 0 rockets with me, 0 cows with me, 0 trees with me. The moment 0 is invented, I have 0 of everything with me. The quantity gets very beautiful. The next question I asked to children is showing 5 fingers. I asked them, how many can you count with 5 fingers? All the kids say 5, uncle. Or some of them might be smart and say you can go on forever. No, but just 5 fingers, how many can I count? I can count up to 31. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. With 5 fingers, I could have count up to 31, right? This is combinatorics. So immediately when the whole civilization thought about numbers, they wanted to then prepare combinations of these numbers and then go on forever. So that is when number system was invented. What does number system have to do with counting? So if I say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if I have 9 ways of representing with my finger, this becomes a digit. And this becomes a digit. This becomes a digit. There's a 5-digit number I have in my 5 hands, 5 fingers, right? So this is how I simplify mathematics for the children. So they start playing with their own fingers, like they do Japam and that kind of a thing. And I tell them how beautiful this country has been to think about mathematics so long and back. So I want to hear from others as well. As time goes by, I see 65 of the audience, right? And I hope my audio is okay and I'm able to share fine all my concepts. So now number system is now cleared. So back in time again we are 2000, 3000 years ago. What is the next thing that humans would have ever thought in mathematics? After finding numbers, after counting things to the heart's content, like, wow, I can count everything now. I'm so happy. I'm jolly. See, give me stars. I can at least put an effort to count. Give me some grains. I can put an effort to count. Give me trees. Give me sheep. Give me cows. I can count. But then what could have then took them to the next step? Can anyone guess? Area, right? Area is a very, very abstract word. Let us just make it even more simple. Geometry, right? Shapes, geometrical shape, not even shapes, right? Straight line. Let's talk about straight line. They would have been interested to know, is there some connection between straight line and numbers at all? They looked at a straight line. How do you think they made a straight line back then? Did they have scale? This is how I talk to children. Did they have scale to make a straight line? How did they make a straight line back in those days? How? Can someone guess? How was the first straight line could have ever been made? Thread. Brilliant. So you have to make something, a thread or a hair or some piece of thing and then stretch. Or you take a vessel and you pour water, it always fills up in a straight line. Right? So that's magical. How how you could have first formed a straight line. But then what was the first need to draw a straight line here and draw another straight line vertically like this? Who could have ever thought of having a vertical line first to make something stand, right? Without falling, they wanted to make something stand like this, right? And then how much angle is this? How much angle is this, right? Can someone type or say? 90. Why 90? Children do not like these numbers at all unless you explain to them why. You say suddenly this is 90, they're like, why not 100, sir? Why not 100, uncle? Why not 100? So they'll say that one whole circle is 360 degrees. So why not 100, 100, 100, 100, 400 degrees? Why 90? So the answer is the sun is in the center. The earth is going around the sun. And how many days does it take to go around the sun? How many days does the earth take to go around the sun? Roughly 365. So they took something very close to that and said 360 degrees because one day you went 1 degree. One day you go like 1 degree around the sun. So then half you go 180, 1/4 you go 90, 45, easy to divide. Just an abstract word. So degrees do not mean anything in mathematics, right? But then somebody said pi, right? Pi, when they talk about pi, they'll be like, oh, it is the ratio of circumference to diameter to this, that, this, right? But just before that, let's go even before that. How do you introduce pi to children? You can look at angles from two perspectives. One is you look at an angle from what is moving. The observer is seeing what is moving and he sees 1 degree move every moment. So 1 degree, my neck is going up, down. When I look at the earth from the sun, if my face is the sun, I'm looking at the earth, I'm looking at 1 degree change every moment, right? But when you look at it from the standpoint of earth itself, that movement, if it moves 1 radius, not towards the sun, it will hit the sun. If it moves 1 radius in the circular path, that is 1 radian. That is 1 radian. That is the conversion between degree and radian. And when you explain to kids this way, their immediate question is, how many such radians are hidden inside the whole circle, sir? How many such radians are hidden? Can somebody guess? 1 hour, you go towards the sun, you will hit the sun. But 1 hour, let's pretend the orbit is circular completely. And let us pretend that the earth is going 1 hour distance the circular path. That is 1 radian, I'm saying. How many such radians are present in the whole circle? Can somebody guess? Can someone guess how many such radians are present? 3.14. Very close, but 3.14 would only lead you from here all the way to here. That's it. Pi is only 180 degrees. Remember? 3.14 is only this much. 2 pi will only bring you back. So there are 2 pi r. That is why the circumference is 2 pi r. So from angles, you connect it to radian. From radian, you connect to the circumference. It stays in the mind forever. So 2 pi is 360 degree because of this reason. Right? Now they start looking at distances. They'll start looking at trajectories, how much you're traveling. It is just not abstract anymore. How beautiful, right? Mathematics is. It is pure art. Teaching mathematics is about painting the brains with a brush and your favorite color, and you're drawing aspects of what you can see, what you can feel, and what you appreciate, right? So these aspects I found it very fascinating to share initially, but then to make it more awesome, right? I'm going to share my screen because I love sharing this to children as well. So I'm going to share my screen again one more time, and then I'm going to show Skyview. So Skyview is another app where I just show the whole universe, solar system, from where the horizon is. You see the horizon, right? And the sun has just set. So of course I am in the west now, and I'm looking up in the sky. I'm looking up for Jupiter and Saturn. I can see them right here behind me in the sky. They are like huge stars. Right now it's a little cloudy in Chennai, but then there are 12 Rashis here, and 12 of them, 6 of them above make it 180 degrees, 30 degrees separated, right? And then 3 or 6 of them below. And the moon is now under the other side, and it's going to come up only at about 10 o'clock. It'll be up here. So you can spot every single object in the space with its time and appreciate geometry and trigonometry, right? So fascinating. So mathematics can be brought to life with simple things around us, which is a phone that I have with me now. So other aspects, right? Slowly we've dealt with number systems, geometry connections to astronomy. What else can we connect to teach children mathematics, right? There are many tools, right? I'm going to pick up, let's say I'm going to pick up a paper, a flat sheet of paper, a square paper. The square sides are 1, 1, 1, 1, all of 1, 1. And now what is the diagonal size? Can someone help me? What will be the diagonal? What will be the diagonal? Namaskaram. What will be the diagonal size if all the 4 sides are 1? Root of 2. And what is root of 2 again?
0.414.
That is an abstraction. That is where we stop. But does it really stop? Does it really stop? Does root of 2 really stop in any calculator at all? A is a side. Okay, but 1, I'm saying A is 1. Just 1, 1, 1, 1. It can be one finger. It can be 1 unit, 1 meter, 1 centimeter, 1, 1, 1, 1, 1. It's an irrational number, right? So it's got no end at all. But then you are able to see it starts and it stops. You keep a scale, you should be able to measure it, right? Why are you not able to measure it? What will your scale show if you measure the diagonal of a square? You're truncating it somewhere, right? You're truncating it somewhere. So you're not entirely measuring everything. Similarly, a circle, it's got 2 pi r in it. The pi is an irrational number. It goes up to infinity. But when an ant walks around the circle, it starts and it completes at the same place. It says, I walked everything. Why are you saying it's incomplete, infinite? It goes up to infinity. Why? Correct? So now irrational numbers are making it very, very awesome for us. They're making us think more. When was the first time do you think irrational numbers were ever encountered, and why? So India is Baudhanya Sutram, right? Baudhanya Sutram is Baudhanya's theorem, which is a parallel of Pythagorean period. So there are sources here, there are shlokas here, there are brilliant references here. Which I don't find much in Greece for any reason, right? I don't find. It's just a group of people there, and there is a story about Hippasus who was taken to the sea and he was drowned in the sea because he told people that the secret that root 2 can never end. But on the same time in India, we were finding 1,000 numbers, rational numbers between root 2 and root 4 with a geometric representation. So our civilization has enjoyed all of this very deeply before, right? And what happens when you enjoy irrational numbers very deeply? What can be a byproduct of root 2? Can somebody guess? Just because you found root 2, what could India have found which is better than what the whole world could have found? Can somebody guess? Why is India very special? Because they found root 2 first. What is special about root 2? Is it just mathematical importance or anything else is hidden there? If you take the number 2, you take it a root and you take another root of it, another root of it, another root of it, another root of it, another root of it. If you take 12 times the root of 2, what will you get? Do you know? If you take a root 2, 12 times square root of it, what will you get? You get a special number, 1.0 dot 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 something. And that number is the geometric progression with which musical notes progress. Sa re ga ma pa da ni sa ni da pa ma ga re sa. I just picked up 7 notes. The 7th one was 2F, F to 2F, right? So that is actually the 12th one on the keyboard. So the whole keyboard, the concept of keys to actually have C, C sharp, D, D sharp and everything, right, is all based out of mathematical interpretation of 2 and root 2. And why is that 2 very important? Because you wanted to double the frequency. We wanted to double the frequency when that transition happened. Because sa, pa, sa, 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 sa. In between that, the magical music was feeling very, very good, right? Because it creates that familiarity and you are able to pattern it. So whole music's origin lies in mathematics. And so we talked about geometry, the Rashi, the beauty of Indian invention of zero, and how geometry connects to arithmetic. Trigonometry is also a byproduct, right? Trigonometry. Excellent. What else can we talk about? Pi, infinite series, calculus. Calculus is a very fascinating subject, right? And who invented calculus? Can somebody help me? Sorry about that. I had an interruption. So who invented calculus again? Can somebody say? Newton, Leibniz. Newton, Leibniz, right? So now I'm going to share my screen, and because this is very important, I'm going to actually go to that particular part of the video. So now, who could have invented this, right? So Mathologer is actually a mathematician who is a very, very popular YouTube channel who used all over the world. Right? He's a brilliant mathematician. He's all over the world, and he's got millions and millions of subscribers, and he talks about fantastic things in mathematics. And I'm going to show one of his videos where he talks about what happens to pi. Who is the first person to come up with pi?
Vinay.
Formula is very beautiful. At the same time, it's very mysterious.
Did you see this?
Think about it.
Can you hear me?
Pi is, of course, the circle thing to do with circumferences and diameters and stuff. On the other hand,
You're able to hear me okay, right?
Earphone.
Sorry, So now I'm going to turn on the subtitles for this. So now, are you able to hear me okay?
Yes, can with some interruptions.
You're able to hear me okay, right? Okay.
Yes, with
So
some
now-
interruptions.
Together.
Between pi and all the numbers. How can somebody mathematically relate pi to all the numbers? Right?
Numbers without a circle hiding within this. His colleague, Stefan Kohn-Voss, is not familiar with this book area formula of the circle. And the absolute and the very by the mathematician Leibniz,
So what does it say?
one of the genius inventors of +1/5, -1/7, and so on. It's usually called the Leibniz formula after Gottfried Wilhelm Leibniz, one of the genius inventors of
Sadly, what does he say? Sadly?
calculus. Sadly, like many other results in mathematics, the formula was not discovered by the mathematician it's named after. At least
So this was actually not the first time invented by Leibniz. Let's
not
go ahead.
first of all. In this case, Leibniz's formula was first discovered by the Indian mathematician Madhava of Sangamagrama in the 14th. At least not first of all. In this case, Leibniz's formula was first discovered by the Indian.
So it was first discovered by Madhava of Sangamagrama. Sangamagrama is a place near Thrissur, where I'm aspiring to visit soon. Right? So you've heard about the Madhava of Sangamagrama. I'm speaking to very nice people from Kerala, right? So I'm so happy to ask this question. So you can think about this place 200 years before Newton and Leibniz minimum, where they have derived the expressions for pi and brought you to infinitesimal calculus, understanding geometry of the space. How beautiful this period of time must have been in India. And Kerala was at the pinnacle of all of this, right? So fantastic. I'm so happy to talk to you all, G, from Kerala, right? So this series laid the foundation for calculus for Newton and Leibniz. So it's a journey. It's a journey that started from there, and then it took a lot of turn and twists and went to west, and then formalization happened with a lot of other series, right? But the Taylor series itself, the sine series, and a lot of this, we have interpretations at here, right? And then once the application started with the physics, right, Europe took over, and we were in a different trend, right? After that, we suffered a little bit. So that's okay. This is just historic perspective of mathematics. So what else? What more do we have to discuss, right? So now there is a huge element of pride involved in being people who pursue mathematics, and being Indians who pursue mathematics, and especially Keralites from Kerala is just, divine. Somewhere the whole divinity is striking upon us from this from the past, saying that pure way of understanding mathematics, right, has existed from back then, using the sand. Why was sand used for mathematics, right? Sand is something you can just erase and re-erase happily. If you see even the zeros invention, right? It's such a magic that I would like to share from my channel. So I'm just sharing my channel with you. So this is how zero was invented. Right? When you have a sand, you're able to see my screen, right? Okay. So guys, what is this? This is sand, right? So in the sand, we're going to start counting. We're going to say one. So we say one by counting. We say counting one by keep a marble inside. There is one sheep. There's one sheep. Now there is one. I'm going to give that sheep away to you. How many sheep is left there? Zero. Do you see why zero got its shape? Do you see why zero got its shape like that? Why did it get the round shape? Why is zero having that nice shape? Right? So these questions it triggers the child's mind. This is when the children know, oh my God, zero was invented like this, is it? Wow. Just when sand, they place the marble, took the marble away, the last piece away, it is zero. So then that is how the digit was actually conceptualized. Right? So now when we teach mathematics to people, we say 1, 2, 3, we lose the zero. So we lose the pride of this number system itself. And then we lose the symmetry, the positive and negative numbers. Why do we have positive and negative numbers? So let's pretend I have 0 cows and you have 0 cows. Can I give you a cow at all? I'm giving you 1. You have 1. How many do I have? -1. I'm going in the wrong direction, right? Negative is nothing but wrong direction. So minus into minus is positive. Why? Because you're making a U-turn, another U-turn. I'm going in the positive direction. Multiplication is nothing but jump counting. How many times you jump and how much you jump per jump makes you the products. And if you have a negative number there, you're going in the wrong direction. Again, division is nothing but equal grouping things into equal groups. You cannot make everything into equal groups, so therefore fractions come. You have a numerator by denominator, it will always repeat in decimals, it will never repeat. If you have irrational number, then it never repeats, and then it goes on forever. So these are stories, right? We are like, it's like a chanting a mantra or chanting your love for what you like. And it becomes very easy to the child. It just completely gets it, and wow, I'm able to understand, right? So might need some more tools to share, right? So I'll share Desmos, 3D geometry, GeoGebra, and all those things. But I wanted to hear from you. Is this session okay, or am I able to help you understand a little bit more? I'm able to share my knowledge better to you.
Yeah, go ahead.
Thank you.
Yeah,
Thank you
please,
so much.
please.
Thank you so much. So now I'm going to give a few more apps. I'm afraid I'm not able to charge my charging point. So I'm afraid that I'll have to request for one more slot if by accident I'm stranded, because I'm just in the campus downstairs. I didn't even bring my charger, and I just realized that my phone is really draining out. So I'm going to stop sharing much and I turn on my battery saver. But then we can make it a little bit more interactive if you can have questions, right? So if I don't touch my screen often, I can go for longer. So now calculus was fantastic. We found out the origins of calculus, applied to physics as well. And now what is needed today? Today, how many streams in mathematics do we have? How much research is happening? How much of that original research is happening in India? Where are the applications of that original research? How do you find out whether or not that research is really original? What do you teach children about what is happening today? How do you teach them? They all say everything is AI. Then what is AI? What are these equations in AI? How can you simplify them as stories to them? Why is everything in AI, engineering, advanced mathematics, everything having a constant called E? Have you ever seen this constant called E, which is the Euler's constant? Can somebody type what is that value of Euler constant and why? Have you ever seen that E? Because every engineering book, anything in advanced science and math has that E to the power of something, E to the power of Y. What is that number? 2.714, brilliant, 73. What is that number? Why is that E everywhere in your books? And E to the power of something is there in every book. Why? Right? So they say it is a natural constant, natural logarithm, natural E, natural exponent. What is natural about this? We have to ask such fearless questions, make children ask such fearless questions. If I give you 1 rupee of money, negative logarithm itself is a very fictitious concept. Exponents, logarithms, and radicals, all the three mean the same. Do not separate them in your mind at all, or the children's mind. Logarithms, exponents, and radicals. Root to the power of and log, all the three mean the same. That is not answering my question for what is E. E is nothing but compound interest. What is compound interest? I give you 1 rupee of money and I tell you 100% interest, you have to give me back the money. You give me back 2 rupees. But if I allow it to compound every 6 months at 50% interest, how much more will I get? I'll get 2.25. Why? Because 1.5 for the first term and 0.75 of that, so 2.25 in return back. I get 2.25 in 1 year. Wow, more. So what will happen if I compound every 3 terms, like 4 months, 4 months, 4 months at 33%? How much will I get? I get 2.34. Hey, more than that. Then what will happen if I do 4 months? What will happen if I do every month? 100% divided by 12. So 1 month, every month there is 8.88%. What will happen if I keep on doing that? If I keep on compounding up to every microsecond, millisecond, femtosecond, where will this one number go to? Can anybody guess? Where will this one number go to? No, it is not infinity. Before it's all the way to infinity, the constant, it will go to E. So 1 rupee of money goes to E given 1 year of time and allowed to compound instantaneously. So that is the magic of E. So now a leaf grows at exponential rate. Heat transfer happens at exponential rate. My hair grows at exponential rate. Everything is exponential. E. Exponent is E. E to the power of something. It also comes in RLC circuits. Everything that relates to the current state to the next state is E. What is 2 to the power of 3? 8. What is 2 to the power of 4? 16. 8 became 16, right? So what you were, you got added to itself. 8 was there and you got added to itself, you became 16. 2 to the power of 5 is 32. 2 to the power of 6 is 64. 32 became 64. So 32 got added to itself. So what you were, you got added to itself and you became more, right? Your increase is what you were before. 2 to the power of x, right? So how, thank you so much. How much you increase if that was the original number itself, that is 2 to the power of, right? But x is only increasing in integer numbers. X is 1, 2, 3, 4, 5. But real world will not increase in an integer form. It will not increase in integer form. So what will happen in the real world? In the real world, it will go up to point not one increase. 2 to the power of x to 2 to the power of x is not 1. What will happen if it increases like that? Will this relationship still hold good? Will you still be able to find out whether my increase was my original number itself? Is it possible for 2 to the power of x? The answer is no. It is true for something else. What is it true for? It is true for e to the power of x. That is why e to the power of x's derivative is e to the power of x itself. So e to the power of x, if you take a derivative, it e to the power of x itself, right? So that is the reason. Why? Because the change itself is what you were before. These are stories. You can go on these stories in calculus forever, right? So beautiful. So children have to appreciate these different equations in their books and different expressions. Y is e to the power of minus kt, this, that, minus n, minus x, minus 5. Wait a second. Or no repair. Yes, sir. So thank you so much. So I wanted to share this piece of information to you. Other than that, is complex numbers I. So complex numbers I is got rotation, right? It's got a rotation. So why do you have a complex number? We have real numbers, right? Why did we have complex numbers? Can somebody explain complex numbers? Why was complex numbers invented? Can somebody say?
Direction. You represent magnitude and direction.
Direction and magnitude. Brilliant. So there's a vector involved, right? So I makes sense only in vector spaces because there is a rotation. Because there is rotation. And why did this I make things rotate? You know, what could have made them think about I as root of -1? Why did they pick up -1, put a root to it, and call it I? Yes, sir. Cartesian and polar both involved in complex number. Yes. So, but why -1? -1, root of -1. Why? So this is the complex coordinate is coming from matrices. So the vector spaces, right? Somebody beautifully said vector spaces are the reason why the matrices were the matrices were beautifully simplified. The rotation of matrices is nothing but I. And when you make a special rotation, when everything goes by 90 degrees, when the matrix multiplication happens, you automatically get I as the eigenvalue. So the eigenvalue is where the whole complex number originates from. But we don't teach that to children. We teach them I is root of -1, root of square root of I, square of I is -1, and so on and so forth. We do not tell them the beauty of where this I came from. So matrices are one beautiful representation. There's a channel called 3 Blue 1 Brown, which speaks like how I do. I learned a lot from them, right? So I wanted to share this with you. That is the reason I had this session. So I'm just trying to think through, right, many other facets of mathematics which might make it very exciting for you for the discussion. Yeah, please feel free to ask foundations of any other concept. E to the power of I. Why would something go and sit on top of E? E to the power of I. Why? Yeah, why is it e to the power of I pi? Why is it -1? Do we know? How can it be -1? So this is called Euler's formula, right? Nobody accepted this formula for a long time. But that is the heart of Fourier transform. That is the reason why I'm able to talk to you now. That is the reason why the signals are getting transmitted. Everything about signal processing, communication, digital signal processing, screens, everything is Fourier transforms. And can somebody explain Fourier transform in very simple words? Philosophically. Has it ever happened to you that you go to office or you go to your college, school, you suddenly meet somebody in the cafeteria and you say, hey, where have you been? I have not seen you for a long time. Right? He's not somebody who you meet every day. You don't know his travel plan, but then somehow you know that he has been missing in your last few weeks. You tell him that, hey, where have you been? And then he says, yes, I've gone somewhere. And then you think, yeah, oh man, I've been smart. I've been tracking you without my knowledge. Without my knowledge, is that possible? How did that happen? Because you had no common points to meet at all, but you still knew that he was in a vacation or he was going somewhere else. How did that come? And what does that has to do with Fourier transforms? Can somebody guess? Frequency to time transformation, right? Excellent. That is the connection. But then frequency is nothing but cycles. That is what I was looking for you from. Frequency is nothing but cycles. The speed at which you rotate, the speed at which you go back home and come back every day to the cafeteria, and the speed at which he goes and he comes back to the cafeteria, even though it is different day to day, month to month, week to week, but you guys have been meeting at some points of time. And then that common points you've been meeting, you've been reinforcing the thought that, hey man, I'm still here, I'm still alive, I'm here. Right? So that is what has happened in e to the power of I pi. So you rotate around the space and you come back to -1. You start with positive, the origin is here, +1, -1. So you go around e to the power of pi. E to the power of pi would have been a circle. I pi makes it a rotation, then brings it to -I. So it is just an interpretation. It is not mathematical at all. If you take a calculator and you put e to the power of I pi, it will go crazy. It will go crazy, right? how fantastic mathematics is, even though calculators cannot perform something, humans have abstracted away and invented something as fascinating as this. And we have the responsibility to teach it well to all our children, all our students, so that they take it forward. So nice to actually discuss this all with you. So anything else that I can throw light on? Any other concepts that has been intimidating us and not helping us easily teach? Something that is not intuitive that you want to think about and tell me. Algebra. How do you introduce algebra? What is the first word you say to them when you say algebra is very important? You don't even say algebra. You say that until now there have been numbers, which we know what it is. Now there is going to be some unknowns. Okay. Variables. And then expressions. The variables are expressing happily. X becomes x squared, x becomes 5x, x becomes x cubed. And then expressions become equations because you have left hand side and a right hand side. So these are the special words that you introduce: variables, expressions, and equation. Once an equation comes, you can have relationships built between one variable, two variable, three variable, calculus, everything comes out beautifully, right? So, zero factorial being one, right? That is, there are nice videos about it. And what is a factorial? Where does combinatorics come? All that is fun fact. They are not very, see, I look for things which are all foundational, which help you in deeper understanding of more important concepts. But zero factorial is equal to one. It's not helped me further, dig through further and help further. But it's okay. It's good. It's a good thing that I saw in one of the videos in YouTube as well, how it is true. Anything else like that? Any other things that can bring an interest in the child for its pursuit in mathematics? So this being said, can I speak a few words about what is wrong in the way mathematics is currently taught? Will I have the luxury to tell to us in a very, very friendly, just suggestions for things we can change in the future? Can I recommend it as well?
Please.
So what is happening today is a concept is introduced in the class, and then there are 10 problems which are solved immediately or in a very short period of time before the concept is completely internalized. And if for any reason the first problem he accidentally gets it right, and he wants to get all the 9 problems accidentally right, and there is a pattern that is building, a wrong exercise, a wrong reinforcement that is happening for the concept. So the reinforcement itself is dangerous when it is not guided. So practice is more detrimental than abstinence in concept in mathematics. Deliberately practicing it wrong is more damage to you than abstinence. So the reason why I find maths very fascinating is because I abstained from it throughout. In an understanding standpoint, I waited until I started understanding everything. I did not understand anything in my younger days. I somehow just satisfied the how parts and just came forward. But when the understanding is tinkered a little bit, and when he's been given problem sets to repeat again and again, he develops a pattern, he or she, and then they start reinforcing that pattern. So practice has to be only in the right direction, and gameplay is very essential for problem solving in schools. Concept is very, very small, but the gameplay is very, very huge. What is gameplay? There are 2 components in every problem. One is called the concept component, other is called the analytical component. The concept component is very, very small and tiny, cute, like how I was just speaking for the last half an hour, right? It's very, very tiny stories. It stays in the mind, it's enjoyable, everything. But the analytical component is puzzles, is scenarios. There is suddenly a ball coming in this direction, there's a trigonometry, there's a calculus, there's suddenly some mass, gravity, velocity. These are all puzzles. Like a crocodile was there, you have to cross the river. And just
Can you please give more insight into the eigenvalues? You just casual reference to it. I think we have lost him.
I think he lost his connection.
Battery getting drained, right? He was talking about his battery getting drained.
Yeah, could have, but I think he has reached his car. He was speaking near his car. That's what I understood. He could have charged from there. I will make a call and see how.
Yeah.
Yeah, I think he lost his power. Yeah. I don't get him, his mobile is switched off. Anyway, that was a good presentation. I think we could get more time on that. And this 1 hour is very short for him. I don't know whether I can give another day for him to explain more. I expect your feedback on how it can be done, because now we are at the end of the year, hardly 3 more talks which are already fixed. I will discuss with him and see whether we can have a longer discussion perhaps 1 hour, 1.5 hours. I want your feedback on that. But all the Wednesdays till January end is finalized. The talks are finalized. Anyway, I will discuss with him, and I please send me your comments on that. How we can. That's a very interesting talk. And actually, for me, I want to know more. That is the one thing which I want to do. Anyway, we will complete the remaining part of the program. Adila?
Yes, sir.
Can someone take a
What?
I will do it. The chat
Hello.
box,
Hello, sir.
Yeah. Adila, you can go ahead with the remaining part of the,
Sir.
even though he is not there, even we will complete the session with the other part of the programs. You can go
Okay,
ahead with in his absence. We will complete it. Later on, I will have a discussion with him and how better we can have another day's talk. Okay, Adila, you go ahead.
Now I call upon Sumaya to deliver vote of thanks.
Thank you, Adla. Am I audible?
Yes.
You are.
Okay, thank you. Now, I, Sumaya, would like to wholeheartedly thank our chief guest, Arun Janarthanan PhD, sir, for his valuable. I would also like to thank our chair, Harindra sir, for organizing and leading this webinar. Also, I express my gratitude to Adla, the moderator, Jacob Verghese, the Zoom facilitator, Amrita Aravind, who delivered the introduction of speaker, Sai Krishna TS, who delivered welcome speech, for your dedicated volunteering. Last but not the least, thank you to each and everyone present here. Thank you. Now I hand over the mic to Adla.
Thank you, Sumaya. Now, next session is on December 1st by Professor Bijuna Kunyu, PhD in PKM College of Engineering, on AC/DC homes, resilience, sustainability, and safety aspects. All the attendees, please try to attend the next session also. That's all about today. Now, handing over to Harindra Lal sir.
So please send me your feedbacks on how we can have another session by Arun Janarthanan. I am for that, but I don't know how we can find a slot. All the slots, all the Wednesdays till January is full. March 14 is the day of mathematics. So I may not be there. That's the main problem. See whether we can arrange that. Anyway, those persons who will be in charge of the webinar can do that. 14th March is a good, or any other day, any other day, Wednesday. That will be better. How about the period, time of the talk? What's your opinion on that? I will discuss with Arun and see how better this can be discussed and introduce a 1.5 hour talk.
So what
And
I-
sorry for the inconvenience to you for this very unexpected interruptions.
Sir, what I think, possibly you
Yeah.
can talk to him and
Yeah.
understand his mind. What are the things he has planned for the day? And based on that, let him decide what is the quantum of time he needs second session.
Yeah. Thank you, Dr. Krishnaswamy. I will have a discussion with him after
Yeah.
the program and see. And I will try it any day other than Wednesday. So that within a couple of weeks when
I
he
think
is
so.
free. I hope.
And also, there should not be long gap between this session and next session, right? So that
Yeah. Okay. Let us
second
see.
session.
Let us see. Okay. Thank you for your attendance, patient hearing, and sorry for the unexpected interruptions. Anyway, it was a very interesting talk. I feel very sorry for that. See you next week with a talk on ACDC systems, ACDC homes by Professor Bijana. See you next week. Thank you very much. Once again.
Thank you. Thank you, sir.
Have a great time.
Thank you.
Please don't close. I want to have a copy of the chat. Okay, Thomas Varghese, you can close the chat. Thomas Varghese, are you there? Yeah, sorry, Jacob Varghese. Jacob Varghese, can close the session.
Yes, sir. Yes, sir.